Dong dong. Hello everyone, it's Mumu time. This time I will take a close look at the theory of how to turn water into vapor and introduce how to convey it away. You may ask, how to convey steam? It's gas. By boiling water? First of all, let's observe the process of boiling water. After water gets enough heat, it evaporates, raises to sky, and becomes a cloud. Everyone have seen it, so I'll start talking about the relationship between them. The main components of air we breathe every second are oxygen and nitrogen. In periodic table of elements, you can find what atomic mass is. Oxygen is composed of 2 oxygen atoms combined to form a stable O2 molecule. So the atomic mass of an oxygen atom is 15.9 times 2 equal to 32 grams per 1 mole. Nitrogen molecule N2 is also composed of 2 nitrogen atoms, 28 grams per 1 mole. The vapor molecule H2O consists of 2 hydrogen atoms plus 1 oxygen atom, 18 grams per 1 mole. The smaller these values mean that the gas is lighter. It's intelligible how clouds floating in the sky. To explain a little, G is gram and mole is the unit of the quantity of matter. If you don't know much about mole, you can imagine that you can unify things into the same unit of measurement. You can make a reasonable and fair comparison. To give you an example, how much does a grasshopper's bouncing power differ from that of a human? We can imagine that if the grasshopper were enlarged to the size of a human, it would be more reasonable and fair to compare. Then H2O vapor molecules will condense into liquid water between normal temperature 0 to 100 degrees Celsius by intermolecular forces called hydrogen bonding, and will solidify into ice below 0 degrees Celsius. If you don't know how much about hydrogen bonds, you can imagine that the H2O is an L-shaped magnet. They attract each other and then condense densely to become water and ice. If you want to learn more about this chemistry-related information, I will put it in the information column for your convenience. We have just made a comparison between gases. So how do we compare the weights between gases, liquids, and solids? This time we will use density for comparison. Density refers to how many kilograms of material are in volume of cubic meter. The smaller the density values mean that is lighter. Density of water is 1000 kg per cubic meter. The density of ice is 916.7 kg. Ice is relatively light. First in our world, you will see ice floating. Air is 1.2754 kg. Clouds are 0.5976 kg. Clouds are relatively light, so we see clouds floating. Back to the question of how clouds appear. During the process of boiling water, water molecules gain heat and gradually move faster, breaking away from the circles of hydrogen bonds to become independent gaseous molecules, break through air pressure, float above oxygen and nitrogen. This is one of the artificial methods to create cloud. In addition, it is worth mentioning that there is a phenomenon in nature that water tends to evaporate due to dry air, which is called vapor pressure or saturated vapor pressure. In short, it is simply like water have a driving force to actively fill up the dry air. This is why water slowly disappears in desert, where it does not have a high temperature of 100 degrees Celsius. So, is it possible to make a long-distance water conveying system by boiling water? Yes, it's feasible if there is enough energy to heat the entire transportation pipeline to maintain the vapor state. However, this method obviously consumes a lot of energy for heating, so it's not suitable for long-distance water transportation. Water pump is much more better than this method. To answer the previous episode question, why does water in high mountains boil at a lower temperature than in plains? This is because water, air pressure, and temperature are closely related. The boiling temperature of water will decrease as the air pressure decreases. If you look further up, when you come to the cosmic vacuum, there is basically only ice and scattered gases H2O molecules, and you will not see the presence of liquid water. In this way, the air is actually very similar to the lid of a pot. It's difficult for the water to evaporate when it's pressed, but the lighter the lid is, or even taken away, the easier it will be for the water to evaporate. Let's read three-phase diagram of water again. Air pressure is 101.3 kPa when we are at low altitude. Follow this line until boundary between ice and water, and look down. You can find that water freezes at 0 degrees Celsius. Continue along this line. This line with the boundary between water and vapor, then look down. You can see that water is evaporating at 100 degrees Celsius. If we come to our design at a higher altitude, air pressure drops to 76.7 kPa. Each line in this kind of logarithmic tables is a multiple of 10. First, the second line from 1 Pascal is 2 and then 3 Pascal. Therefore, 76.7 kPa starts from 10 kPa and come to the middle of the 7th and 8th lines, which represent 75 kPa, and along this line until the boundary between ice and water. Looking down, the water is still freezing at 0 degrees Celsius, and continue along this line until the boundary between water and vapor, and then look down. You can see that the water evaporates at 90 degrees Celsius at this time. There is no air in the reverse at all. Air pressure is 0 Pascal. If you look directly at the bottom line of this table, you will find that there is only ice and steam. Liquid water is absent at this situation, and the junction between ice and steam is minus 60 degrees Celsius. So, the statement about the minimum temperature in the previous episode is based on this table. In reality, you need more advanced insulation tools to do it. Not an insulated coffee cup can do it. Speaking of the universe, by the way, let's take a look at our neighbor, Mars. Its air pressure is less than 1% of the Earth. The average air pressure is 400 to 870 Pascal. Average surface temperature is minus 63 degrees Celsius, and the highest is only 33 degrees Celsius. May I ask you, is there liquid water on the surface of Mars? The answer can be found on Wikipedia. The bits and pieces that we are accustomed to on Earth may seem like a matter of course. But when we look at the solar system, water, enough air, and warm sunlight are actually precious resources. When everyone drinks water and basks in the sun, please think about it. All resources that exist on the Earth at the same time are hard-won and need to be cherished. Back to question, how to produce steam by using vacuum. I compare the process of boiling water and vacuuming together. When boiling, Water gets enough energy from heat source and breaks through the hydrogen bonds cycles. Part of it becomes vapor, then breaks through air pressure to rise to the sky and become a cloud. On the other hand, vacuum pump removes air pressure, then water can evaporate by its own energy, and easily break through the hydrogen bond cycles to turn into vapor. In the second part, let's talk about the phenomenon of heat absorption and cooling of water under vacuum. Why temperature drop of glass bottles and pipes is observed when water is vacuumed? As explained in the first part, water can only choose between boil or condense in a closed environment with a vacuum of 1 Pascal. In fact, at this time, it will have another behavior. The vapor pressure of water in this vacuum environment is very high, because the vacuum pump continuously pumps out air and water vapor. In other words, water is forced to quickly turn into vapor to fill the space that is constantly being pumped away. And the freshly made vapor is also constantly taken away. In order to achieve the goal of quickly evaporation, water needs more additional heat than its own to help with boiling transition. So water constantly absorbs heat from glass bottles, pipes, and remaining ice to become vapor. This is how the phenomenon of heat absorption and cooling by vacuum water occurs. To answer, why does continuous vacuuming of water cause freezing? It may be caused by the evaporation of water by absorbing heat from nearby substance in order to quickly fill the vacuum that has been pumped away. This phenomenon can reasonably be inferred that faster the vacuum pump pumping speed, water boiling speed may faster, and more heat is absorbed. If the most environmental friendly energy, solar heat, can be added as a heat source to provide additional energy for water conveying, desalination, and power generation system mentioned in the previous episode, it's likely that the evaporation rate of water can be accelerated and the efficiency can be greatly increased. Finally, I'm going to make up for an experimental short film that could not be put down in previous episode. Observing experiment of the ultrasonic mist maker added to the vacuum water conveying system for everyone's reference. A brief explanation. In order to keep the vacuum airtight, I put 24-volt DC charger in a plastic bag and the ultrasonic mist maker into an evaporation glass bottle together to eliminate chance of air leakage caused by while causing this vacuum environment. The experiment was a small success, although it can be observed that the vacuum pump discharged a small amount of condensate. The effect of the single-head ultrasonic mist maker is not obvious, and the amount of atomized water and the amount of discharged water cannot be specifically compared. So I hope to get your support, PayPal or remittances to sponsor me to do experiments and continue to study these phenomena and applications. I have a question for everyone at last. Do you think humans can turn deserts into forests by relying on the vacuum solar long-distance water conveying system? Please tell me in the test area. 水滴石穿，以油制缸 Be water, my friend.